All right, so we want to do another truth table to sum of products canonical form. And this guy is a 4 variable function, so it's a little bit more beefy, right? It's got a little bit more to it. But that said, our sum of products canonical form, it's a nice cookie cutter method that we could do to a billion variable function, and it's still the same. It's not super difficult to do, just a little bit more tedious. So once again, our first step here is to identify all the rows where the output is a 1. So we got 3 more here. And now we need to list them using the sum of products notation here. So that means we've got a not, right? Because all of these are zeros. And so if they're zeros, that means their variable is knotted for this term in the function. So we've got a not, b not, c not, d not. And remember, I'm not putting the and signs in there, but we know that if you have 2 variables pushed together, that means they're ANDed. And we also know for our sum of products canonical form that they're all ORed together. All the products are summed together, or ORed. So we're going to OR. And then our next term here is, here I'll just do a little check mark to keep track. We've got A not, B not, C, D. Got that one. Then we've got A not, B, C not, D. All right, that's that one. Then we've got A not, B, C, D not. There's that one. And then I'm going to kind of roll over here to the next row. We've got A, B not, C, D, ORed with, oops, there's that. We've got a cat meowing, and we've got A, B, C not, D not. And our final term here, we've got A, B, C not, D. So there we have it. That's this function represented mathematically, right? So this equals x. So there's one way that we can show this. The other way that we can show it, right, is through a shorthand notation, right? So we could really go either way here. So let's do our shorthand notation. So that means we're going to start off with a sigma here. I'm going to do it in purple. So we've got sigma, and our variables, which are A, B, C, D. We have to have the variables on there because otherwise if we list numbers, we don't know what context or what variables this function is describing. And then we need to know our row numbers. So let's go through and label these real quick. We got 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, and 15. So what rows do we have? We've got 0, 3, my 5 doesn't look very good there. That's a little bit better. So 0, 3, 5, 6, 11, 12, and 13. So there's our shorthand. And you can see that this is a little bit more portable. Like if I was sending an email to my boss and I need to describe a truth table, I'd probably choose this form right here because otherwise everything else is kind of a little bit more nasty. And this tells us all the information we need to know. The other more hardcore way to display this function right now is using a logic diagram. So it's a little bit goofy, but let's do that. So oops. So we're gonna kind of go down here. Let's see what this looks like. So we've got 1, 2, 3, 4, 5, 6, 7 AND gates. We've got 7 4 input AND gates. Oops, there we go. So let's make those. So we've got 1, 2, 3, 4, 5, 6. No, it's gonna be tight. But there's our 7th. And so I could draw a bunch of NOT gates on here, but something that's handy to do is actually just bubble the inputs. So we, for this first one, we want to bubble all 4 of them. So that's A, B, C, and D. And here, so let's put our bubbles in first. So we've got the first 2 are knotted, and then every other one's knotted here. I realize this isn't the most clear, but just to kind of show you how overdramatic some of these can be when you do the circuit diagram. Then we've got the exterior ones knotted, and then just one of them knotted, and the bottom 2 knotted, and finally just that guy knotted. So we could bring. I'm not gonna do it because it's just gonna take too long, be too tedious. But you can see that I would take A, link it down. B would get linked down, so on and so forth. All these would get linked. So that's kind of what that part of the circuit would look like. And then we'd have a big friggin' OR gate, and all these guys would link into the OR gate, and that output would be X. So that's what these sum of products expressions always look like as circuits, is they just have some AND gates with some inverters before them and fixed certain spots, and then that all goes to a big OR gate.